So using this. So for example, example 9.2.6. Example 9.2.6. So let M to Z be a ring of all. Let M to Z, M to Z, M to Z be the right of all. Be the right of all. Right of all. 2 cross 2. 2 cross 2. Matrices over Z. Matrices over Z. Matrices over Z. Under addition and multiplication. Under plus means addition. And multiplication. Multiplication means nothing but star. Let Z. Let S equal to. Let S equal to. Let's see. A0, 0B. A0, 0B. A comma B belongs to Z. Belongs to Z. Is a subgroup of M to Z. Subgroup of GP means group of M to Z. So Z means 2 cross 2 matrix, nothing. So solution. For A0, 0B, comma, C0, 0D. Let this 0D. It belongs to S. 0 belongs to S. Where A comma B comma C comma D belongs to. Where A B C D belongs to Z. That means set of integers many. So we have A0, 0B minus C0, 0D, 0D. That's equal to A minus C, 0, 0, B minus D. Subtraction of 96. So, which is belongs to S. This belongs to S. Where A minus C, comma, B minus D belongs to S. Belongs to S. So B and B minus D belongs to Z. Set of integers. Set of integers. Their product. Here subtraction we did. We need to do product. Product means A0, 0B and C0, 0, D. So this is nothing but multiplication of matrix R1 C1 plus C plus G. R1 C2 0. No? R2 C1 0. So R2 C2. But here, which belongs to S. Here AC comma BD also belongs to set of integers Z. So S is a subring of M to Z. What we conclusion? Let S be the subring of M to Z. M to Z. To Z. Next. Further, for any PQRS, further any PQRS belongs to M2Z. 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 So here PQRS belongs to PQRS or nothing but set of integers belongs to them. And A00B A00B belongs to S, belongs to this. A comma B belongs to Z. So we have PQRS. So product of two PQRS into ABCD A0 0B that equal to nothing but multiplication of matrix R1 C1 PQ PA R1 C2 R1 C1 R1 C2 PB RQB QB R1 C1 R1 C2 next R2 C1 means RA next SB which does not belongs to yes. If QB is not equal to 0 or RA is not equal to 0 because if we are comparing this means this matrices we get PQ QB is not equal to 0 or RA is not equal to 0. So and here opposite A0 0 A0 0B into PQRS into PQRS AP R1 C1 P R1 C1 R1 C2 AQ and R2 C1 PR next R2 C2 yes which is does not belongs to yes. If AQ AP is not equal to 0 or BR is not equal to 0. So therefore S is not a ideal of M2. S is not a ideal of M2 by definition of ideal. So CYP means check your progress. Question number 1, same method, right for homework. Already solution also is there. Right. Next, theorem, 9.28 theorem. The intersection of any two ideals of a ring are the intersection of any two ideals of a ring. Two ideals a ring. Ideals of a ring Ideals of the ring. Intersection of any two ideals of the ring R is again an ideal of R. Is again ideal of R. Ideal of R. Ideal of R. Proof. Proof. Let I and J be ideals of the ring R. Let capital I and J be two ideals of R. Ideals of R. Ideals of R. Then previous theorem 9.2.7, 0 belongs to 9 and 0 belongs to J. 0 belongs to J by previous theorem 9.2.7. And therefore 0 belongs to I. 0 belongs to I intersection J, intersection B. So that I intersection J is non-empty subset of R. Yes, non-empty subset of R. Non-empty subset of R. Let A comma B belongs to I intersection. Let A comma B belongs to I intersection J. Then A comma B belongs to I. And A comma B belongs to J. And A comma B belongs to J. A comma B belongs to I, and I is an ideal of A comma B belongs to I. Then I is an ideal of, and I is an ideal of that implies A minus B belongs to I. A minus B belongs to I. Similarly, A comma B belongs to J, and J is an ideal of, that implies A minus B belongs to J. A minus B belongs to J. So here A minus B, here what we are, A minus B belongs to I, and A minus B belongs to J. What we conclude in these two, because here A minus B belongs to, we can write I intersection J. I intersection J. So small r belongs to capital R, comma, A belongs to I. A belongs to I. A belongs to I. Then ideal is, and I is an ideal of R. I is capital I. Is an ideal of R. An ideal of R. That implies RA belongs to I. RA belongs to I. And RA belongs to I is nothing but left ideal, that is. AR, this is right ideal. This belongs to I. Similarly, R. Similarly, R belongs to capital R. Uh, capital R. Small a belongs to J. And J is an ideal of R. That implies RA belongs to J and AR belongs to J. AR belongs to J. So, in these two, what we conclude here, AR belongs to I and RES. This RA. RA belongs to I. Left ideal, right ideal. We can write RA. We can write RA. RA belongs to I intersection J. Similarly, AR belongs to I intersection J. I intersection J. So hence, I intersection A is by definition of idea. I intersection J is an ideal of R. Now this completes the proof. Hence proof. Here writing means, Right. Next. Go for next theorem. 9.2.0. 9.2.0. Important theorem. 9.2.10. If R is a commutative ring, statement. If R is a commutative ring, R is a commutative ring. R is a commutative ring, and small a belongs to R. Small a belongs to R. Then I equal to R belongs to R. R belongs to R. Is an ideal of R. Ideal of R. Ideal of R. Proof. For 0 belongs to R. 0 belongs to R. Now 0A equal to 0 belongs to capital I. Therefore, I is not equal to 5. Not equal to 5. And I subset R equal to capital R. Let X comma Y. Here, let X comma Y belongs to I. Then X equal to RA. Y equal to AR. So R1A, R1A, AR2. R1A, R2A. For all R1 comma R2 belongs to capital R. Right. So X minus 5. What will that? That implies X minus 5 can be written as R1A minus R2A. You take R common. What is inside? R1 minus R2. That is that equal to R of A, which is belongs to I. I means ideal. Since R1 minus R2, which is belongs to capital R. For X belongs to I. And Small r belongs to capital R. Small r belongs to capital R. Small r belongs to capital R. Comma. X dot r equal to R1A. 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 Comma. R. Comma R. That equal to R1. A R. That equal to R1. R A. Nothing but left ideal, right ideal. Which is commutative, since R is commutative. Commutative property for multiplication, nothing but A and B equal to A, and AB equal to B, like that. That implies R1R, R1R, A belongs to I, since R1, R2 belongs to capital R. Since R is commutative, Rx equal to XR. Since R is commutative, commutative. Rx equal to XR. Rx equal to XR. Therefore, X belongs to I. X belongs to I. R belongs to capital R. Capital R. That implies XR equal to Rx. That belongs to I. So thus, capital I is the ideal. Capital I is an ideal in R. Ideal in R. Similarly, R is a commutative ring. A belongs to R. Similarly, if R is a commutative ring, commutative ring, commutative ring, commutative ring. A belongs to R. A belongs to R. Then belongs to R. Then I equal to. Then I equal to. A R such that R belongs to capital R is an ideal of R. Is an ideal of R. This completes the proof, hence proof. Which proof means hence. Next, definition. 9.2.15. 1 definition. 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 If let R be a non-trivial commutative ring, let capital R be non-trivial commutative ring, then non-trivial commutative ring, non-trivial commutative ring. This identity, an ideal I, is identity. Identity. An ideal I of R and ideal P of R is called principal ideal. Principal ideal. Principal ideal of R, capital R. I equal to AR such that R belongs to capital R. For some elements, element A belongs to R. It is denoted by within the square bracket A. Means this is what is called principal ideal of R. So every ideal of R is a principal ideal. Every ideal is a ideal of R. Is a principal ideal. Here, principal ideal. Principal ideal. That is, can be noted I equal to within the square bracket. For all small a belongs to capital R. So capital R is called principal ideal ring. Then capital R is called principal ideal ring. It's called ideal ring. It's called ideal ring. So using the definition, we'll prove one theorem. Most important. That is 9.2.14 theorem. 9.2.14 theorem. The statement, the ring Z of integers, the ring Z of integers, integers is a principal ideal ring. It's called ideal ring. Principal ideal statement. Fourth. So triplet Z plus star is a commutative ring with identity. It's a commutative ring with identity. Commutative ring with identity. And it has no zero divisors. And it has no zero divisors. No zero divisors. To prove that every ideal of Z is a principal ideal. RTP. RTP means required to prove. Every ideal of Z is ideal of Z is ideal of Z is principal ideal. Ideal. Principal ideal. let I be an ideal of Z. I be an ideal of Z. If I equal to 0, 0, then OZ, and hence I is a principal idea, and hence I is a principal idea. I is a principal idea. The principal idea. Next page. Principal idea. Suppose I is not equal to. Suppose I is not equal to. Not is not a null set. Not equal to 0. Then there exists a 0 is not equal to A. Then there exists symbol. A is does not belongs to A. 0 is does not belongs to A. Is belongs to I. Not equal, not 0 is not equal to 0. Not equal to I. And we have 0 is not equal to me. And we have 0 is not equal to minus A. Minus A. This belongs to I. Since I is an ideal, yes, I is capital I is an ideal. I is an ideal. So A belongs to I. That implies minus A is also belongs to I. Because integers. Therefore, either A or minus A is positive integer. I hence a set of positive integers of I is non-empty set. Hence, by well ordering principle, we have smallest positive integer I left it. The smallest positive integer. Smallest positive integer. A0. We shall prove that I equal to A0. Required to prove. We need to prove RTP means required to prove. I equals to A0 star then. Star then. So I is an ideal. So I is an ideal. I is an ideal. I is an ideal. And A0 belongs to I. A0 belongs to I. We have that A not Z. A not Z. Subset are equal to I. Subset are equal to I. Let X belongs to. Let X belongs to I. X belongs to I. Then by division algorithm in Z. Then by division algorithm. Division algorithm. In Z. Division algorithm in Z. We can write. We can write. We can write X equal to A naught Q plus R. This is nothing but dividend equal to divisor into quotient plus remainder is there now. That is the factor theorem. Remainder theorem. Person for Q comma R belongs to Z. R belongs to Z. Q comma R belongs to Z. Q comma R belongs to Z. With 0 less than or equal to 0 less than or equal to less than A naught. Less than E. We have A naught belongs to I. A naught belongs to I. Q belongs to Q belongs to Q belongs to I. Q belongs to I. Q belongs to Z. Q belongs to Z. I is an ideal and I is an ideal. I is an ideal. That implies A naught Q belongs to I. A naught Q belongs to I. So X belongs to I. X belongs to I. A naught Q belongs to I. Belongs to not Q belongs to I. Not belongs to I. That implies X minus A naught Q belongs to I. R is not a positive. R is not a positive. That implies R must be equal to 0. R is not a positive. R must be. R must be. That implies R must be. R must be equal to 0. Equal to 0. Must be equal to 0. R must be equal to 0. So, R must be equal to 0. 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 So therefore X minus X minus x minus n, x minus n, x minus a naught cube equal to r. That implies x minus a naught cube. R must be equal to 0, no? That will put 0. That implies x equal to a naught cube, a naught cube equal to a naught cube. Hence, a naught is the smallest positive integer in I. Hence, a naught hence a naught is the positive, smallest positive integer in I. A naught is the smallest positive integer in I. Smallest positive integer in I. That implies R must be equal to 0. So x belongs to, hence x belongs to I. X equal to a naught cube. So Q belongs to Z. So Q belongs to Z. A naught cube. A naught cube belongs to A naught cube belongs to A naught Z. A naught Z. Therefore, I equal to. Therefore, I equal to. Therefore, I equal to A naught cube. A naught cube such that Q belongs to Z. Q belongs to Z. Such that A naught Z. A naught Z. And hence I equal to A naught Z. A naught Z. Thus, every ideal of I. Thus, every ideal of I. Ideal of I. Every ideal of Z. Of Z is a principal ideal. Yeah. Principal ideal. Principal ideal of Z. Principal ideal of Z. And hence Z is a principal ideal thing. And hence Z is a principal ideal ring. This completes the proof. Hence proof. H proof means hence proof. Next. Next. Quotient rings. Next, quotient ring. Quotient ring. Quotient ring. Definition. Quotient ring. Definition. Let R be 9.3.2. Let R be. Let R be a ring and I be an ideal of R. Let R be a ring of the element. IB an ideal of R and IB an ideal of R. Ideal of R. Then R by I. Then R by I equal to means defined like that. A plus I such that A belongs small a belongs to capital R. With respect to induced operations, with respect to induced operations of induced operations of addition and multiplication. Addition and multiplication. Cosets defined. Cosets defined. Cosets defined by cosets defined by A plus I into plus B plus I that equal to A plus B. I plus I, 2I is nothing but I. And A plus I into B plus I equal to AB plus I. Because I plus I into I is not I square, I square is I. So A plus B into I. For A plus I, comma B plus I belongs to R by I. R by I. R by I. Where A comma B belongs to capital R. Where A comma A B belongs to R. This ring R by capital I, comma plus, comma star is called quotient field. Quotient field. Of R. Quotient field is called quotient field. So, example. Consider the ring jet. Consider the ring jet. Consider the ring jet of all integers. Of all integers. N jet is a positive jet of an ideal of jet and ideal of jet. Ideal of jet. Then the set of all cosets of N jet. Then the set of all cosets of N jet. In jet is Z by N jet. That equal X plus N jet. X plus N jet such that X belongs to Z. X belongs to Z. So that is the set of all distinct sets. That is the set of all the set of all distinct cosets. Distinct cosets. Cosets of NZ. NZ is Z by NZ that equals 0 plus 0. 1 plus NZ. 1 plus 2 plus NZ plus so on N minus 1 plus NZ minus 1 NZ. Then Z by NZ plus into means nothing but triplet object. Forms a quotient rings. Forms a quotient ring. Quotient ring. Forms a quotient ring. In this ring, observe 0 plus NZ is nothing but NZ. Is the zero element of element is the zero element and 1 plus NZ 1 plus NZ 1 plus NZ 1 plus NZ is the multiplicative identity. It's the multiplicative. Mi means multiplicative identity. So easier. So one more important. I have to do 9.4.1 exercise theorem or problem 9.4.1. Because we don't have time. Next. Definition 9.2.16 definition 9.2.17 EG means example and 9.2.18 theorems. 9.1.8 theorem. These are most important. So try to do as former. Okay, dear students. Thank you. Thank you very much. I'm leaving. Time is over. I'm leaving. Thank you.